So far, all of our examples have been systems at equilibrium. In the first example, the trunk was not moving at all, so it was having static friction force, but it was still at equilibrium. In the second example, Joey was moving, but he was moving at a constant speed, so he was also at equilibrium. We can also do problems with inclined planes that are not at equilibrium. And we're going to do an example like that now. This is typically as hard as two-dimensional forces get. So if you need to come back and watch this video several times, please do so. As always, we're going to start with the free body diagram. We have a person with a weight of 625 newtons skiing down a hill that's sloped at 36 degrees. And they're giving us the coefficient of kinetic friction, and they're asking for the acceleration. So right there, that means the system is not at equilibrium because the skier is accelerating. So let's look at our free body diagram. There's our slope. Here's our person. And their weight is 625 newtons. There is a normal force. And there is a kinetic friction force because the skier is in motion. And this angle is 36 degrees. So now we can break our gravity, our weight force, into x and y components. FGX and FGY. And again, don't worry if your drawings don't really show a right triangle, because this is definitely not a right angle, as long as you understand what they're supposed to show. If it really bugs you, you can erase them and redraw them. But I put the little symbol there so I know what it's supposed to be. So now we have our free body diagram. And we have all the information that gives us. And now we can talk about what this means. So the sum of the forces in the x direction. This is the skier. The skier's accelerating, and their acceleration's going to be down the hill, right? Logically. So the sum of the forces in the x direction does not equal 0. This is the first time we've had this. The sum of the forces in the x direction equals the net force. Because really, when we've been saying the sum of the forces in this direction, we've been talking about the net force in the x direction. So the net force is equal to, and I'm going to say down the hill is positive, so this FGX minus the frictional force, because that slows them down. And we know that the definition of net force is the force that causes the acceleration. So mass times acceleration equals FGX minus FFK. And we know the whole point of this is to solve for acceleration. So we can even further say that acceleration is equal to FGX minus FFK divided by the mass of the skier. So right there we've derived the equation we need to solve this problem. We need the x component of the weight, which we can get with our triangle, and we need the frictional force, which we could get if we had the normal force. Because remember, we were told that this is 0.17 And we know equals this times this. So we need to get the normal force. We can talk about the forces in the y direction as well. Now, even though there's motion and acceleration in the x direction, in the y direction the skier is still not moving or not accelerating, right? So they're not floating up in the air or sinking into the snow. So the sum of the forces there still equals 0, which means FGY still equals our normal force that we need up here. So this was a lot more information that we got out of our drawing, but it's the same thought process. We just got here, and we said what our net force is, how we calculate it, and then we said what our net force is equal to, and you guys all know F equals m times a. And I just went ahead and did the math, because I know that we're solving for acceleration. So our next step is to find these x's and these y's. Now I'm going to resketch my triangle right here so that we can see it. And we know that this is 625. And this is our FGX and our FGY, and this is 36 degrees. So if we want to solve for our x, it is opposite. So we're going to use so. The sine of theta equals opposite over hypotenuse. We can calculate that our FGX is equal to 367 newtons. And I'm not going to circle it because it's not my final answer, but I'm going to underline it so I can find it easier in a minute. And now I want the y, which is adjacent, so I'll use co. So cosine of theta is equal to adjacent over hypotenuse. And we get that FGY is equal to 506. Now, because of our logic steps earlier, we know that FGY is also equal to Fn, and FGX plugs into this equation. So now we need to find our frictional force. We know that the frictional force is equal to the coefficient times the normal force. And we're given in the problem that the coefficient is 0.17 times this 506. So we know our frictional force is equal to 86.0. Now we have this, it's our Gx. We have this, now we need our mass. This one's pretty easy because we know our weight is 625, and we know that weight is always mass times acceleration due to gravity. You don't have to show this work if you don't want to, but we would do 625 divided by 9.8 to find that our mass is 63.8 kilograms. So we can now plug into this equation we derived much earlier. And we can say acceleration is equal to FGX minus FFK divided by our mass. When we do our math, we get that our acceleration is equal to 4.4 meters per second squared. So this one is a lot of work, and it all stems from that logic. So if you need help with this, go back and study the stuff in the dark red, where we looked at our free body diagram and we found the information. And then after that, it's just plugging into equations that you know and are comfortable with and are familiar with. Try the practice problems below, and please ask me if you need help. Come to office hours. Let me help you figure this out.